Okay, so I'm Yusen, I work for Geoscience Australia, and today I'm just going to show you a little bit about our national coverage of AEM, and then I'm going to do a zoom in to the GP2 area and try and show you a little bit of how we go about interpreting AEM, and I've got some more sections and things if anyone wants to have a closer look at anything that could be of interest to you. All right. Anyway, that's a pretty picture of what the plane would look over some of this continent that, as we know, is covered mostly by some sort of cover, which is usually conductive. So thanks, Faith, for Phil, for setting the scene. The difference between potential fields, which is mostly what we're used to, probably the gravity and the magnetics, is that those give us a single point over a certain area. The electromagnetic, you have to think of it like a smoke ring that is diffusive. It goes into the earth, it polarizes the ground, and you have a two-dimensional response, which you don't have from the potential field. So then you have a true sense of depth, which you can really not get from the potential fields. Righty. Okay, just a cartoon, so you can see we have a transmitter, which is on the fixed wing aircraft, around the wings of the aircraft, and then a receiver, which is measuring the secondary fields in the receiver, and those have certain geometrical characteristics that need to be modeled and measured in order to have a correct interpretation of the conductivity. So that's just the context. We can also have a helicopter, and we have used both these systems, and there's a plethora of systems out there. At GA, we try to quantify the response, so we've moved away from just bump finding in the profiles to real modeling of conductivity and quantitative analysis of true depths. So through time, GA has developed a lot of inversion codes. They're designed to deal with real problems in acquisition. We solve things around geometry and parameters. The problem with AEM data and inversion of AEM data is that a non-unique problem. So there's multiple responses that models that could give you the same reading. It's the same with a lot of geophysical techniques, but the more measurements you have on the geometry and things like that, the more true you are to your conductivity model. Most of our codes are 1D, which means we assume that the Earth varies vertically, but it is within a footprint that is determined by the geometry of the aircraft. And that holds true for about 90% of the cases. We also have, all our codes are free, that you can access them and anyone can access them. We have a GitHub repository. We have parallelized them to run them on the NCI, which stands for the National Computational Infrastructure. And most of our codes we run on the different lines for curation of the data and to try and extract the greater bit of analysis we can from them. They have lately been uptaken by a lot of academic, other government users, and very likely by industry. We have some requests of compiling them in the super clusters in North America, especially some of the Canadian companies, but they are there for anyone to use. Okay. Just a little bit of I want to show you a little bit of what the differences are. So on your left is what we call a deterministic, which is one model which is tried to be solved by the algorithm and gives you the best fitting model, right? The other three on your right, what we've called here the P10, P50, and P90, is a broad range of models, all which fit the data. So instead of having one model, we're assessing the data sets with 100,000 models per sounding. So that gives you a robust statistics on what you're resolving. Much more credibility on your model, at least you're testing things to the limit, right? And then you can do all sorts of interpretations, as we have here on the right. Righty. Okay, I've talked about the codes. So just again, as Phil Heath suggested, conductors are usually what we're targeting. Inductive methods highlight conductors, and conductors can be salt water, massive sulfides, clays, and the resistors are usually, you know, the crystalline bedrock or fresh water. So just a very quick run through history. What we call the AEM, or the Australian Wide Acquisition Program. It's the biggest program of its kind. We started back in 2017, and that looked big. That is kind of the size of some of the small countries of Europe. Then the program expanded. We moved into the Northern Territory. Of course, we know geology and its geological features and properties don't care about boundaries. We have changed the flight direction. We usually try to intersect the geology perpendicular. So that's the reason why you can see that's a north-south trending lines. Then we moved into WA. We covered the north. The Western Australian government got excited and they got some funding. So they co-invested with us and we started going south. As you can see, the coverage expanded. We started using fixed wing and helicopters, or a combination. Because of our modeling capabilities, we generate seamless maps, so it doesn't matter the instruments that you're acquiring the data with. And the picture starts to look really promising. These are 20-kilometer separation lines, but you can see the great trends and you can see interesting features there. Yep. As you can see the Gilgan. Then we went even further west. Then we flew what we called the Eastern Resources. That covers parts of South Australia, New South Wales, and another bit of Queensland. This was a little bit more challenging because of the greater increase of infrastructure and population, of course. And then again, in 2003, we kind of flew our latest piece of the puzzle, and that's the GP2 and a lot of the nullable planes, which is what I will be doing a little zoom into. So what can you really resolve at 20 Ks, right? And of course the GP2 was flown at every 5-kilometer separation. And we were questioned about this, but people forget that the magnetics, we have one of the best geophysical data sets in the world. If any of you have explored in any other countries, you don't just go and get magnetics or gravity. Governments don't provide that, so GA has done that for a long time, and what you guys have access to is sort of because people had the vision of doing this a few years ago, and those data sets are worth millions of dollars, right? So it started that way, and Phil's talked about the 7K gravity. That's how we started, and we've started zooming in. So maybe we'll do the same with the AEM at some point, still to be known. But what I'm going to show you now is a little bit of the Yusen Lee-Cooper. That's a nice picture of the plane flying over the bight. And come on, there you go. What I'm showing you here, and that takes me back a little bit to Rowan's comment about artificial intelligence. I don't like the term. I don't think there's such thing. We train the data sets. at GA, I'm very skeptical about the machine learning things. We need to train the data sets and get correlations, but just let the things run. I'm quite skeptical. This is a grid of conductivity of the near surface where we fed, I know exactly what we fed the algorithm to train the data sets. And the main driver is the conductivity of the AEM, the very near surface. It's a beautiful image. You can see it's being guided by radiometrics, satellite, DMs. So what we're trying is to fill in the gaps between those flight lines. All right? So it's a trained interpolation, let's say. And why that little image in the bottom, though it's a bit pixelated, I apologize. It shows the footprint of the aircraft, right? So at surface, when you're flying these machines, these instruments, you are sampling about 100 meters in diameter, right? And that diffuses up to tops 500 meters depth. But, so we have to have these things in mind. You're not going to find grandma's ring that she lost in the paddock with an AEM system, although the principle is similar in the sense we are trying to detect conductors, right? Right. So I took this from a publication that will be talked about, and it's really interesting because I don't know the area much from geology, but what I'm going to do is showing these interpretations which are based on bores, trying to show you how you can expand that knowledge and kind of draw from the AEM, hopefully. So I'm highlighting a few things that are of interest for me that I think are coming up on the AEM. One are one is this feature here, the clay layers that are under the Wilson Bluff limestone, and you'll see in the next few slides. So basically, I'm showing you 3 lines of conductivity, right? These are west of the border, but I picked them because I think they're interesting. And then one is coming into the GP2, and those are the lines. So these lines are available, and anyone can download them, and you can see the sections. So let me see what I think we might be able to resolve. So I'm going to fade away. So this is the Euclid Nullable. I think these are the Baxter Cliffs. You can see the more conductive region here in the row plane has limited depth of investigation. This is a line going north, that is 40 Ks. That's the Nullable plains. And it's interesting, this is the Wilson Bluff zone. And if you remember from the previous image, the drill holes come down to roughly 300 meters. That's around the same area. I'm not saying these are exactly, we're matching the lithology, but they're definitely markers that are coming up on the conductivity. So it'd be very interesting to really spend a couple of weeks looking at these data sets and seeing what they mean. Also, some of our colleagues in the Nullable were thinking these little pockets could be freshwater. But what is really interesting is going up north, close to the GP2 area. Like, look at the job the AEM is doing there. Those are the sand dunes, of course. There's a marker. And then you can start seeing how it gets complex and all the breaking of the clays and accumulation up there. All right? So just a teaser of that. Now I've rotated it, so I'm looking south. That's the bite. And the line I'm going to show you is here, just very quickly. That's what the line looks like. Okay, what does that mean? So what we do at GA is we generate these multiplots. What are these multiplots? So that's your section that goes roughly up to 500 meters. That's the data as it's acquired. This is the level of fit. We're trying to hit 1, and there's places where we can't fit the data. That's okay, that's honest. But what's interesting here, I think, in this part of the world is that magnetic high. And why I say it's interesting, because that's in a conductive environment, which we've seen in other parts of the world with high accumulations of salt water or brines or other things kind of seem to concentrate the heavy metals. I'm not saying go drill this line, but I think there's some stuff worth to follow. We've got 3 more slides to go. I'm going to show you another line that I thought was interesting. That's again south. So it's the very extreme, and you can see the paleo channels really neatly defined. So again, the multi-plot, and look at these confined conductors. We're fitting the data. They're about 400 meters. I would go and test that. There's some interesting features there. I don't know if the geology is correct. It's prospective geology. I haven't gone that far, but I think these things are pretty interesting for follow-up. Okay, so just to finish, this is our coverage so far. I really think we need to extend our vision and unveil the geology just way beyond what we can sample at surface on outcrops and through drilling. I hope you see the value of AEM, and that's the program so far. That's all I have for you. Thank you.